So we're going to have a look at two examples. Now the first example is f of x equals x squared minus 4. Now you know what this looks like, it's a parabola, but we have a restricted domain. Now why has the domain been restricted? This allows us to turn the function into a one-to-one function, which means that it will then have an inverse. Have a look at these sketches which illustrate this. So if we sketch f of x equals x squared minus 4 for an unrestricted domain, we know that it would look like this. It's a parabola with a y-intercept at -4. So there's no restriction on the domain here, which means that this is currently not a one-to-one function. It is in fact a many-to-one function, which currently means there is no true inverse. Now, in the second sketch diagram, we're going to restrict the domain of f of x to x greater than or equal to 0, which means we're only allowing x to be greater than or equal to 0. So that means that our function looks like this. Now, this means that it is now a one-to-one function, so an inverse function will exist. An inverse function will only exist if the original function is one-to-one, or if we restrict the domain of the original function so it becomes one-to-one, which is what has happened in this example here. So what we're now going to do is take this function and we're going to find the inverse function. So what do we know so far? We know that f of x is equal to x squared minus 4, and its domain is x is greater than or equal to 0. Now, what about its range? A lot of you have been asking, how do you find the range of a function? Well, sketching the function is an excellent way of identifying the range, either by hand or on your graphical calculator, because the range refers to the set of y-coordinates that are allowed or that exist for that specific domain. Now, which y-coordinates are allowed? Well, we're allowing y to be -4 or anything above -4. Look at the x-axis. Can you see as it stretches outwards, you keep generating larger and larger y-coordinates, and in fact you're allowed any y-coordinate apart from anything below -4. So the range is very simply y is greater than or equal to -4, and your range should always be in terms of y or the f of x, it should not be in terms of x. So let's now find f minus 1 of x, and that's quite easy. So let's set y equal to x squared minus 4. Interchange x and y, so x equals y squared minus 4, and then this rearranges very easily to give us y equals the square root of x plus 4. And this is the inverse function. So f minus 1x equals the root of x plus 4. Now, even before I sketch it, I will know the domain and the range because, of course, we know they switch over. So the domain of this function is that x is greater than or equal to -4, and the range of this inverse function, we'll write the range in terms of y. You could write the range in terms of f minus 1x, and that would be correct. I find that it helps people to avoid making mistakes if they just put the range in terms of y. Y has got to be greater than or equal to 0. So we know that square root graphs look a little bit like this. So the graph is going to have this sort of shape when we sketch it out. No, its lowest x value is -4. So it starts there, and we know it's got to be a reflection of y equals f of x in the y-axis. So it's going to look a little bit like that. So this purple graph is y equals f minus 1 of x, and we really should draw a graph of y equals x to show the reflection. So here's a sketch of y equals x. So to find the range of a function, sketch the graph using the given domain and have a look at which y-coordinates are feasible. And the domain and range of a function and its inverse are reversed. And you can see that from the diagram of information over here. So I've picked another example which was on the recent half-term homework, which quite a few people asked about. F of x is equal to ln of 1 minus x, and again we have a restricted domain here. X lies between -1 and 1. So the first thing that I want to do is find the range of this function, so I need to sketch its graph. So I can do that on a graphical calculator very easily, but I'm actually going to think about this in terms of a series of transformations. It's quite interesting for us to do that. So let's think about the graph of y equals ln of x, first of all. So we know the graph of ln of x has an x-intercept of 1. The y-axis, the negative y-axis, is an asymptote. So the graph looks like that. It's quite a good sketch, if I do say so myself. So y equals ln of x. Now, the next thing I want to think about is this transformation that's occurred here. I'm going to rewrite this as y equals ln of -x plus 1. Now we have to be careful here because this is a transformation of this format, ax plus b type of transformation. And if you remember from the work on combined transformations, this is the one transformation that doesn't behave the way we expect. We look at it, and because we're so used to order of operations in BIDMAS, we feel like we want to do the stretch part, the ax part, before we do the translation, but actually it's the other way around. So we actually need to do the translation first, and that's with a vector of -1, 0. And you could think of this as a stretch in the x direction with a scale factor of -1, but a more common way of thinking about that is to think of this as a reflection in the y-axis. So both of these affect the x-coordinates, but the translation has to happen first. So that's the first thing we're going to sketch. So remember, the y-axis, in particular the negative y-axis, effectively took the role of an asymptote here. So that's now going to move one place to the left as the graph is translated to the left by one place. We no longer have an x-intercept of 1, we have an x-intercept of 0, and the graph takes exactly the same shape, just looking like that, 1 unit to the left. So this is the graph of y equals ln of x plus 1. And the last step, of course, is to reflect this in the y-axis. So now, if we're reflecting in the y-axis, everything is mirrored. So I want to put in this line here to help guide with the asymptote. And the graph will still pass through the origin like this, but of course it will be in the other direction. A little bit trickier to draw this. So it will look a little bit like that. So this is the graph of y equals ln of 1 minus x, or -x plus 1. So now from here, how do I find the range of the function? Well, we were given some information in the question which told us that the domain had been restricted to -1 to 1. So that means the domain of the function is represented by this yellow set of x-coordinates. So how do we find the range? Well, if x is equal to -1, what is this y-coordinate here? Because that's as far up as we can go. Well, if x equals -1, y is equal to ln of 2. And keep that as an exact value. Nobody needs to see random decimals here. So that's as far up in the y direction as we're allowed to go. But can you see, for all of these x-coordinates going up to 1, we're allowed any y values at all. So as you get closer and closer to 1, the y values just become more and more negative. And you cannot substitute 1 into the actual equation. If you try it, you get ln of 0. Now, some people tried to put that in as part of their domain, but there is no defined value of ln 0. It just doesn't work. What you have to do is use the graph. And again, I emphasize this. As x increases, getting closer and closer to 1, look at the y coordinates. They just keep becoming more and more negative, so the graph just keeps carrying on down. So you're allowed any y coordinates you want in this negative region here. So the range of this function is that y is less than ln 2. After that, y can take any value it wants to as you go below ln 2. We're not allowed ln 2 as a y value because, of course, in the original domain, x is between -1 and 1, but not equal to -1 or 1. So now let's find the inverse function. So I'm going to set y equal to ln 1 minus x. I'm going to switch over x and y. So x equals ln 1 minus y. And then we're going to rearrange to the form y equals. So e to the x equals 1 minus y. And from here, we can say that y equals 1 minus e to the x. So what about the domain and range? So we know that f of x equals ln 1 minus x. We know that f minus 1 of x is equal to 1 minus e to the x. Now let's identify some domains and ranges. So the domain and range, first of all. So the domain of f of x equals ln 1 minus x, we were given this in the question. You're usually told the domain so you can work with it. So it was -1 to 1, not inclusive. And what about the range? Well, we worked it out. Y is less than ln of 2. Y can be any value below ln of 2. So that tells me that the domain here is going to be x is less than ln of 2, and the range is going to be y is between 1 and -1. Now again, you can sketch this to have a look at the shape of the graphs. So what does the graph of 1 minus e to the x actually look like? Well, let's take a look at the graph sketching of this. So what does e to the x look like? First of all, it looks like that. So that's a graph of y equals e to the power of x. Now, what about negative e to the power of x? Well, that is a reflection in the x-axis. So that will, of course, look like this. There was a y-intercept of 1 there, and that's now a y-intercept of -1. And then, of course, you have to add 1 as well. So we translate this with a vector of 1, 0. So the final sketch will give us the graph of y equals 1 minus e to the x. This, of course, is y equals -e to the x. So translating up by 1 unit, previously, in both these cases, the x-axis was the asymptote, but the line y equals 1 now becomes the asymptote there. We had an x-intercept here of -1, but that's going to be translated up 1 to the origin. So the graph will look like this. So that is the graph of the inverse function. But we have a domain, which is that x is less than ln 2. So the graph must be restricted by that point there. And the y values are between -1 and 1. So there's your y value of 1. And this must be a matching y value of -1. So the yellow portion of the inverse function is the graph, stretching back up towards the asymptote for negative values of x.